Okay. So, hello everyone. We have with us a very special guest today. So, he's Atiqur Rahman. And something a little bit about this speaker. He's pursuing his PhD in the University of Cape Town regarding pulsar astronomy, focusing on using pulsars to analyze and search for stochastic gravitational wave background. So, he's going to talk about his research work today with us. So, here's the floor to you, Atiq bhai. And I hope you guys enjoy his talk.
Thank you, Tasnova. Uh, Thank you for the nice introduction. Okay, everyone, I'm Atiq, and today we will be talking about two things. One is, uh, let me, where is my, yeah. I hope now you guys can see me as well. Uh, okay, let's start. So we'll be talking about two things. One is galactic clocks, by which I mean pulsars. I will tell you why in a little bit. And number two is gravitational waves and how they are related and how we are using the pulsars to detect gravitational waves. Um, I'm doing my PhD here, and this is my topic to my research topic is basically using pulsar timing array. I will explain what that thing is to detect an alternate, to basically saying that can we detect an alternative theory of gravity's mode. Okay, so this is my research group, very handful of, I mean, a great team. Everyone is very nice here, and I love to be here with this group. They're very helpful. And on the right side, you can see that how I'm connected to BRACU. All these people are like, I had amazing time uh, at that time when I was going to Mahubsar and Tibrosa for my research. And I also met my life partner there, so it was kind of a place for me. Okay, so these are the things I want to cover today. First thing is, what are pulsars? What are gravitational waves? I will refer them as GWs from here. And what are pulsar timing arrays? And what can we do with it? And what is the current status of this whole research field? So let's start with what are pulsars. So before knowing pulsars, we need to know about neutron stars. What are neutron stars? Neutron stars are extremely dense remnants of a neutron star, massive star. So whenever a massive star blows up, uh, at some specific case, we get a neutron star. So anytime the star becomes more heavier than like 8 times or higher than our sun, we get a supernova. And at the core of the supernova, we get something called a pulsar. It's a very dense core of the dead star. And we'll see the properties of that star very soon. So first, we need to understand that how a star stays stable throughout its lifetime. So there's two different forces acting on it. One is the gravitational pull towards its core, and the other is the radiation that comes from the fusion happening at its core that is going outward. So when these two stays in balance, the star is in a stable system. But as soon as the fuel is about to finish, the uh, balance is no more, right? There comes the instability, and that is where our research actually starts. As soon as the instability starts, the star starts to collapse, and at some point the supernova happens, and then we get the highly dense core. Here we can see one of the example. Here we can see on the left the Crab Nebula. And at the very center of it, we can see there is a pulsar. And that pulsar is called crab pulsar. You know why it's named that. But you can see that it is spinning, and we can see the uh, field around it, all the fluids around it, all the dust particles around it is like in a rotation. And there's also two jets. One is going into two opposite directions. Now, about neutron stars, how dense are they? What are the radius are like? So for any neutron star with a mass of like 2 or 3 times the mass of the sun, it will get squeezed into a 20-kilometer radius. So if you compare it with any city of Earth, it will be like, if you think about Dhaka, it's like, you can see I just tried to create one on top of Dhaka city. It's like from one side South Shahar, another one is like Narayanganj. That is the radius, barely. And on this, if you pick up any amount of mass, as much as like one teaspoon, it will be 1 trillion kilograms on Earth. So it is like highly dense object. Uh, why we call it a pulsar? We call it a pulsar because it keeps pulsating. So basically, what happens when the star collapses, due to its internal mechanisms, it starts creating a magnetic field around it, and on the two different poles of the magnetic field, it uh, opens a jet of all the radiations, right? So if you let me just try to show you. Sorry. I forgot to put that extra animation here, but I'll try to explain uh, that what happens here. So you have a spherical shape, and on its two different poles, you get a jet each side, and that jet has all kind of frequencies throughout the spectrum. Um, so it radiates energy throughout the spectrum, and that is the name pulse. The name pulsar comes from uh, another property that has to do with its its rotational and this magnetic axis. So it has a rotational axis and it has a magnetic axis. And rotational axis and magnetic axis are not aligned. They have a like angled situation. And this, when this one rotates 360-degree, this one also creates a cone around the sky. And that cone, if we are on the line of sight of that highly magnetized pulse, we see it once a while, and it looks like something is like pulsating to us, like a pulse a second, something like that. That is from there the name pulsar came from. And this effect of giving a pulse, also called a lighthouse effect. The reason is here. You can see that when a lighthouse lights up and rotates around it, after a certain period of time, it looks like the light swaps around us. And that is why it's called a lighthouse effect. Now, this is also interesting to know that how pulsars are discovered. Pulsars are discovered by this PhD student called Jocelyn Bell in 1967. She was doing her PhD at that time and working on creating a radio telescope. And she figured out that, okay, this telescope has something unique here. It got some signal, and that signal is a periodic signal. So they thought maybe some outer species sending us a signal. So they named it the little green man. And later they realized, okay, this is no species, this is not aliens. This instead is something else, some dead star. These are some other photos of and for this discovery, her PhD supervisor and someone else, I forgot his name. They got the Nobel Prize few years back. So we want to observe pulsars. Wait a second. Oof, I don't like this. Okay. So pulsars we can observe on the radio frequency side of the spectrum, which is like high wavelengths situation. And I have three different uh, animation here that can give you a sound. I mean, whatever frequency it has, it converts it to a sound wave so that we can hear and understand how fast they are. So the first one, not all at a time. Sorry, I want to start one at a time. So this one is one pulse at a time. It's like per second, something like that. And this one has like 11 times a second, so it is much faster. But we are much more interested in this kind of ones, which is like 650 times a second. So it's very, very fast. Sorry for your, sorry for all the trouble in your ear. Okay. So now the question is, why are you interested in such fast rotating stars? Now you can also ask me the question, why are they rotating so fast? The reason being is like each star is rotating, and when it is collapsing, it needs to conserve its momentum. So what it can do, it can just increase the rotational speed. And that is what it is doing. And how much mass it had and how much it has now after being a pulsar, that is where uh, it says that how faster it is rotating per second. So that is our first part of the talk. Now, for the second part, we are going to discuss what are the gravitational waves. So for that, uh, we want to know what are black holes or other compact objects. When this kind of objects collide into each other, they create a ripple in the space-time, and this ripple can be sent at the speed of light. There's two different modes we call polarization modes of the GWs. And they show that how it can squeeze and stretch into different directions while passing through. Uh, and this one, of course, was predicted by Einstein in 1916. Here we can see one of the animations where two compact objects, you can say two black holes, two neutron stars, whatever it is, when they start rotating each other, they create such kind of ripples in the space-time. And it affects everyone on their way. And it should go in all directions. So yeah, here's another simulation created by NASA. Uh, you can see that at the very moment when the two black holes collide to each other, there is a high intensity wave goes through the space-time. So when I said polarization modes of the GWs, what do I mean by that? How can I get the mathematical structure of it? So basically what you need to do is to linearize Einstein's theory of relativity and use a certain gauge called traceless transverse gauge. And then you will get these H plus and H cross modes. And they can be expressed as a sine and cosine waves or combination of them. And if you do that, you will get two different modes. And if you plot them, you will see plots like this, where this plot actually denotes that if you have a unit mass across a certain radius and the gravitational wave is passing through it, how this wave will impact their relative distance between them. Now, do you remember LIGO? LIGO discovered GW around 2015. And what happens is this stretch in one direction and squeezing in other direction, they take benefit of this property of these modes, and they created two light beams across 4 kilometers from each other, and at two different places. One is Hanford, another is one is at Livingstone, and they try to compare the distance between these two, and this two hand of the LIGO detector, and they found a relative change in the length of these two things, and that gave the first detection of the GWs. And what kind of distance we are talking about here? We are talking about a distance of like 1/10,000 of the width of a proton. So yeah, so it is very, very sensitive. So we need extremely precise measurement of whatever we have. All the instruments needs to be very, very precise. So it's very, very, very challenging in the engineering way, and also the analysis part of it is quite difficult. Okay, now I forgot to say, not, I didn't forget, but I forgot to add an effect here. So this is what I am trying to do. Okay, so here are the analysis results from the two different detectors at two different places, and then plotting one over the other. Now you can see that there is no change, no change, no change, and slowly the change increases, and then there is no change again. So basically what happens when the two black holes comes as close as possible, the ripple starts happening, and at the very moment when these two collides, there is a maximum amount of signal that it can produce, and then it goes to the universe. Okay, now there is two different I mean, there is a whole spectrum of GWs, right? One detected by the LIGO, which is the high frequency GWs, that is in kilohertz. And there is also a low frequency wavelength and low frequency GWs, which we can try to detect using a new technique, which is called the pulsar timing array, which is our research field. Now, what is a pulsar timing array? A pulsar timing array is a set of pulsars across Earth in around 1 kiloparsec distance. So what we do is we try to calculate the time of arrival from the pulse to Earth, and we can do it pretty accurately. And that is why pulsars are called highly stable clocks of the universe. So if you discover a pulsar today, and you track it down for like 3-4 years, you exactly know that when the next pulses will come for the next 10-20 years. You also can detect the change of the period over time, so that you can keep correcting whatever you are predicting, whatever period you are predicting in the future. You can just do simple calculations to get the exact time period where it should be at which point. Now, here is a nice depiction of what I'm trying to say. So there's one fact that I forgot telling you, that every galaxy has a supermassive black holes at its center. And when these galaxies are merging together, the black holes are also merging, right? And whenever this kind of massive objects merge, what happens? There will be a ripple in the space-time. Basically, GWs will produce. Now, there will be more than two galaxies in the world which are merging at the same time, or merged in near time. So everyone produced their own GWs, and they will uh, interfere with each other and create a gravitational wave background, which is basically a statistical form, like thousands of GWs are produced and they are added to each other. Now, what happens is pulsars are much more closer to Earth, which is like 1 kilo per second away, and galaxies are much far away. So what happens is whatever pulses they are trying to send us, this pulse will come through this space-time, right? And if the space-time is curved, it will take uh, some time deficit to fulfill the distance between the pulsar and the Earth. And we are trying to measure that difference. Here's another plot created by Rowena from Australia. Uh, so you can see that this space-time is curved, and now the pulsar in the I think the color is purple. Okay, so you can see that it takes a longer path only because the space-time is curved. So we are just trying to find out what is the difference that it takes due to these GWs in the background. And if we can figure out that what is the difference in time, then we can use that time to say that, okay, now we know that there is a gravitational wave background. But there is more to it, because there is not only two pulsars, there is not only one, sorry, there is not only one merging black holes, one set of merging black holes, and not one pulsar. There is a lot. So here you can see that around the Earth, there is a lot of different pulsars. Each data point in the left is a pulsar, and each trying to send a signal. And scientists from 70s or 80s, I forgot exact date, they did this theoretical work where they said that if you have a set of pulsars and you calculate the correlation between them when there is a GWB in the background, there must be an angular correlation between them. So how the how much more the effect of the GWB will be is defined by the angular separation between them. So the lesser the separation, much more the correlation will be. And at the middle, at the 90-degree-ish region, there will be less correlation or anti-correlation. It will be correlated negatively. And then around 180 degree, it will again start picking up the correlation. And we are trying to figure that out, that how uh, we can use this theory and use this pulsar timing array of ours to find these things using our available data. Here is a data set. Here is a result basically, which published in last year, where we had like around 83 pulsars in our data set, and we have a 4.5-year data set. So we analyzed the data and we saw that, okay, our data is very close to the theoretical plot line here. So that with few other pulse timing array groups around the world showed that yes, they also found this thing, and we are very hopeful that we will very soon be in the detection zone of this uh, long wavelength GWBs. And these are other results from the other pulse timing arrays. So yeah, that is all from my side today. Uh, what I am uh, what I want to tell you is like what I am working on right now. So there's two polarization modes that I talked about in this short talk. One is H plus, another one is H cross, according to Einstein's theory of relativity. But if you want to modify the theory, if you go to the modified theory of gravity side, then you can get at max 6 different polarization modes, and not all of them are detectable using pulsar timing arrays. What happens is one of the polarization modes, it's called scalar transverse mode, and we are trying to detect specifically that one using our recent data set. And the problem is it needs more sensitivity of our instruments. Like we have quite a good number of radio telescopes around the world, but none of them are yet sensitive enough to get that amount of data or that sensitive data uh, that can detect that kind of signal. And if we can detect that kind of signal, then we can say that, okay, general theory of relativity is not the right theory. Some other modified theory is. And if we cannot, then surely that is a test for the uh, Einstein's GR. Yep, that's my time, I guess. Any questions? Anyone?